Okay, in that case, I'll be starting the second StarPU lecture now. Just a moment. Okay, so now I can start. Okay, so for the second lecture, the learning goals are basically just to learn a little bit more about StarPU and then understand how StarPU support distributed memory and understand how StarPU support GPUs. Unfortunately, due to time constraints, I cannot really go to any details how to do distributed memory computations in a StarPU. I will be just showing you a simple example, and the same goes with the GPU support, because there is, especially with the GPUs, there is a lot of additional complexities involved there when it comes to performance models and deciding how you actually cut the computations in suitable size chunks to have a task that can run well both on the CPU and on GPU, so that the runtimes you can actually do some form of reasonable decisions based on that information. And there simply isn't time today to cover that. That should probably require, both of these topics might require their own training course to really cover them properly. And hence I will be just showing them, giving the overall idea at the end of this lecture. And instead of concentrating on giving you necessary tools to actually write the StarPU program that has data dependencies between the tasks. And these data dependencies are handled using data handles and data interfaces. Because as mentioned earlier, you should not use these task arguments for anything that requires data being moved between the tasks. They should be only used for arguments that stay static. And because of the fact that they actually be static, they do not generate any kind of data dependencies. And that's why all the data that should generate data dependencies and thus task dependencies should be packed inside the data handles. And the data handles are kind of abstract object that is specified with the type StarPU data handle T in the StarPU API. And it could at least theoretically encapsulate any conceivable data type. So you can implement the data type implementation yourself to tell StarPU what sort of data it is and how it should be moved around from GPU and, for example, distributed memory. There is an API for that. But there are built-in data types for scalar values, for vectors and matrices, and then there are also more complex ones for different kinds of sparse matrix presentations that are really handy if you're doing a sparse arithmetic. And these are in most cases enough. So if you want to create a variable data handle, so data handle that points to individual variable, then you can call StarPU variable data register. So you are registering the data with StarPU, so StarPU knows that the data may generate data dependencies between the tasks. And the first argument is just that you're passing to a pointer to this StarPU data handle T object that is then going to be initialized by its function. Then you have to specify what is the home node for the data. So you have to tell StarPU where the data is located at this very moment. And in most cases, since it is the main thread that is generating tasks, then the data will at the beginning reside in the main memory of the computer. And therefore you're telling it StarPU main RAM is the location of the data. Then you may pass a pointer that will contain the initial value of the data handle. So if you have, let's say, integer, then you would pass a pointer to the integer here. And the last argument is the size of the variable. And because the variable data type is meant to encapsulate any type of variable, the StarPU doesn't actually care if it's an integer, if it's a float, if it's a struct, or even if you're passing a vector as a variable. It doesn't care. You just have to tell it where it's located at the moment, where it's located at the moment, and what is its overall size. And this is a function that gets called by the main thread that is inside the tasks. And inside the code task implementation, you can then use these two macros to fetch the relevant information from the interface that is passed on to the task implementation. So you can use StarPU variable get pointer. You can get the pointer that is valid for the task implementation. So the pointer can point back to the original variable that you initialized if you run it on the same machine on the CPU core, or it can actually point to a GPU memory, where the StarPU has guaranteed that there is a valid copy of the variable for you to use. And in case you might sometimes also want to fetch the element size, because that might sometimes be variable as well. But with the variables, usually what you want to pass on is just a pointer, and you want to get access to it inside the task implementation, so you can do some computations with this particular variable. And for vectors, it's very similar. It's StarPU vector data register, and again, it is just this opaque data handle where all the information is going to be stored. Then we give the home node, we give a pointer, and the only difference is that this time we want to specify what is the length of the vector, and the element size is going to be the size of the individual element in the vector. And then in the task implementation, you can request a pointer to the beginning of the vector. You can request how many elements this vector has and what is the size of the individual element in the vector. And the same goes for matrices. Again, the same thing, except that now we also have to specify the linear dimension. We must specify the dimension of the matrix to the direction where we have linear dimension. And then we also have to specify the second dimension. By default, it assumes that this is a C program. It assumes that we are storing the matrices in row major format. So in that case, the nx would be the number of columns in the matrix, and linear dimension would also be in that direction, and ny would be the number of rows in the number of columns in the matrix. And then we have this matching. Once we can get the pointer, we can get the nx and y, we can get the linear dimension and the size of individual element of the matrix. And again, reminding that StarPU kind of assumes that everything is in a row matching order, where the argument x is the width of the matrix and the argument n is the height of the matrix. Whereas in the hands-ons that you will do later today, we are storing stuff in a column major format, which is much common with the plus and layback libraries. And there in your head, you must remember to swap the x and xy with each other, so that the nx is absolute number of rows in the matrix, and that is also the one for the linear dimension, and ny is the number of columns in the matrix. And then just let's look at a simple example where we have initialized a matrix at some point. So we are just calling malloc to allocate with columns, and then we have linear dimension number of rows for each column being allocated, which is a really standard way of allocating the matrix. And then we have this StarPU data handle, and we are calling StarPU matrix data register, and we are giving pointer to this data handle. We are telling it that the data currently resides in the main memory. And then we give a pointer here, and we just have to convert it to uint ptr t type. We will tell it the linear dimension. We will tell it the height of the matrix, so the number of rows in the matrix, and then we will tell the number of columns in the matrix. And the final thing passed on to this function is the size of the individual element in the matrix, which is in this case just a double precision number. And what is happening here that in the main thread, it has this pointer that points to the beginning of the memory buffer that stores the matrix. And now we have associated with the StarPU data handle. So StarPU knows that somewhere in the memory there is a matrix that is being stored in a particular pointer, and the application thread itself knows that StarPU has some internal data structures that store information about this matrix, and we can go and access it indirectly through the data handle. And once we are then done with this particular data handle, we always must remember to unregister it. So if you call StarPU data unregister, what this does, it will wait until all the associated tasks have finished executing, and then it will copy the data, if necessary, back to its original location, and then free the data handle. So after calling this function, you can then go and freely use this original variable inside in your main thread. And there are several ways you can pass these data handles to these to different tasks. But you can, for example, have a static number of them. You can have variable number of them up to a certain limit, or you can have an arbitrary number of data handles. And when you want to have more complex situations, you have to write a little bit more code. But during this course, we are assuming that we have a static number of data handle passed to each task to keep things more simple. And so what you have to do, you have to code the codelet that told StarPU what sort of task it is. And you have to specify the n numbers field that tells how many data handles this task is going to accept. And then you have to specify something called StarPU data access modes here. And you note that there is this maximum number of buffers that can be passed on. If you need more than that, then you have to go and do something slightly more complex. And to learn how to do that, you have to look at the StarPU user's manual. And now going back to the access modes. So there are several different access modes defined. So the first one is StarPU none, and this is something that is undocumented at the moment. It's used for internal use. It is probably indicating that there is no data handle in this particular element of this array here. Then you can specify that the data handle is going to be read-only. So this is comparable with the depend clause in. Then we have StarPU W indicating write-only, and is comparable to the depend clause out. And then we have StarPU read-write indicating that this is a read-write data handle comparable to the depend in-out clause. Then you can also specify that it's possible that data handle is used as a scratch space. So it should not generate any data dependencies, but it sometimes makes sense to let StarPU to allocate the necessary scratch space for the computations. Then there are several specialized access modes. For example, you can specify that this data handle is used in a reduction operation. So when you're combining the results from several different tasks, you may want to let the StarPU do the necessary reduction operation. Then you can specify that this data handle can be accessed in an arbitrary order, and this allows StarPU to execute the tasks more freely. And but it still means that only one task can access this data handle at a given time. It is just that the task can do this in arbitrary order. Then we have some access modes that relate to how the StarPU MPI functions. And also we can tell the StarPU that this data handle's content is very sensitive in locality sense. So you can tell the StarPU that it should take such things into consideration. But during this course, it's just StarPU read, StarPU write, and StarPU read write are the ones that are actually relevant here. So let's go and look at some example. We have a codelet here, and the first thing we have here is, of course, the final CPU implementation for this codelet. And then we are specifying that this task is going to accept a single data handle, and the access mode for this data handle is going to be read-write. So this task that is generated from this codelet will go both read and write from this data handle. Then when we insert a task using a StarPU task insert, we know that we have to, of course, pass a pointer to the codelet. And then we will specify that we have a data handle that is read-write, and then we will pass on the data handle to it. And you will note that there is some level of redundancy here where we are specifying this read-write twice. That just comes from the way StarPU ended up being implemented. So you have to pay some attention here that you actually have the access modes matching the modes that you are specifying for the StarPU task insert. And in case of the actual task implementation, what you do there is that you will initialize a StarPU matrix interface. And this interface is now going to correspond to the data handle that again is connected to the initial pointer that you initialize while allocating the matrix. And this buffers is going to be an array of void pointers. So we'll just take the first element from this array, and we will just go and convert this pointer directly to a pointer that points to a StarPU matrix interface. And after we have this interface, we can then use StarPU matrix get pointer to get the pointer to the matrix. We can get the height of the matrix, we can get the width of the matrix, and we can get the linear dimension of the matrix, all extracted from this interface. And then we can just call whatever routine we want to go and operate on this matrix. So there is this kind of decoupling happening where in the main memory somewhere, the main thread has initialized this matrix and connected it to a data handle. And then some magic is happening inside StarPU. And when we go from the StarPU to actual the task implementation, it is going to get this matrix interface from the StarPU, from which the worker thread will then extract the corresponding pointer to this matrix. And if it's all running in a shared memory without GPUs, then these pointers are usually exactly the same. But if this task happens to be running on GPU, then StarPU will internally copy the data to GPU's memory. And in that case, this pointer here will actually point to a copy of the matrix that has been automatically copied to the GPU's memory. And then let's see what happens if we have two tasks that are accessing data handles. If we have a situation where both tasks are accessing data handles in the read mode, then of course there is no data dependency between these two tasks, and they could run in parallel, as explained before. But if this first task would now go and have a read-write access to the second data handle, and this data handle is then later read by the second task, now StarPU will, from this information here, deduce that there should be a dependency between task 1 and task 2. Therefore, task 1 must be executed before task 2 can be executed. And now we are coming to this hands-on that is somewhat more involved because there are now so many components that needs to be moved around. So I would like to go and modify this example here below and add some additional code to it. The first modification is that you will write a new task implementation called add CPU that accepts 3 data handles that are all variable backed inside the variable data handle that are type int, and they are sent in the arguments buffers 0, buffers 1, and buffers 2. Then you will go and extract the corresponding interfaces from there, the variable interfaces, and then you add the 2 first arguments together and store the result to the third data handle. And then you will add the corresponding codelets, and again, reminding you that you have to set the data access modes in a correct way. And then in the main routine, you will create the 3 variables. You will register a data handle for all of them, and then you will insert 2 tasks, and in the end, you will unregister everything and then print the variables out to confirm that you have really computed things in a correct way. And I have a solution available for here to see how it's actually happening. And now I will come to 2 remaining points during this lecture. The first one is just to give you an overall idea how StarPU handles distributed memory. So the distributed memory stuff is can implement on top of MPI library, and you can do it in 3 distinct ways. The first one is that you will just ignore StarPU's own MPI interface. So you write your own code that is going to interface with the StarPU with the MPI directly. And what you have to do is that you have to copy stuff manually between the data handles and the buffers that you're actually sending or receiving over MPI. And there is a routine call that allows you to temporarily acquire a data handle. And this means that the master thread will wait until all related tasks have finished, and then go and promise you that here is the data at this moment in time. You are free to do whatever you want with it. And then you can do MPI send or receive, and then you can release this data handle to let StarPU continuous combinations with the data handle. And this is generally not recommended. I don't see any proper reason to do this in this way, except if you really quickly just have to hack in a distributed memory support for your code, or just want to implement part of your code in a task-based manner of StarPU. But otherwise, this is just loads and loads of additional work to do all this copying explicitly. The second approach is to use StarPU MPI. And what is basically happening here is that in your code, every time you see MPI receive or MPI send, you will just go and replace them with the StarPU MPI receive detached and StarPU MPI receipt detached. And these pretty much have the same kind of interfaces as the receive and send calls in MPI, except instead of accepting pointers, they will accept data handles directly. So you just go and insert tasks as before, and every time you want to communicate something to a different node, you will just receive and send, but then on just pass on the data handle to StarPU MPI. And then StarPU MPI will underneath the hood talk with the MPI and send the actual data over MPI library. But perhaps the most interesting way is to use StarPU MPI using so-called MPI task insert utility. And this actually requires only a minimal number of changes to be done to convert your shared memory StarPU program into a distributed memory StarPU program. And the first step you have to do is that every time you're inserting a task using a StarPU task insert, you replace it with the StarPU MPI task insert. So it's just telling StarPU that this is actually a task that is going to be involved in some sort of distributed computation. And the second change you have to do that every time you register a data handle, you also have to tell it, you also have to register with StarPU MPI. And there you basically just tell two things. The first thing is who owns this data handle. And the second one is that for each data handle, you must give it a unique tag, which is just an integer number. And these integer numbers should be the same across all MPI processes. And that is the way how StarPU knows what handle is what it encapsulates what data. In case of the second and third approach, StarPU will allocate one CPU core for the MPI communications. So you will lose one core, and that core is then continuously checking if it has some data it could send or receive over MPI. And in the third approach, it is the data dependencies and the data distribution that can be automatically used to generate the necessary communication pattern. So as before, I used the example, let's say there's node number 0 that knows that it is supposed to execute this task here, and it needs some input from two tasks that came before it. And it knows that this first task here has been executed node number 3, and it knows that the second task has been executed node number 1. So it knows that it should do a receive call from node number 1 and node number 3. And node number now knows that it has executed this task here, and it knows that this task here needs its output. So it knows that it has to do a send to node number 0. So there is corresponding send and receive pair happening here underneath the hood. And the same thing goes for node number 3. Once it has executed this task here, it knows that node number 0 is going to need the output from this task. So it will do a send, and node number 0 will do receive. But this is all happening automatically and asynchronously underneath the hood, which is very nice. And the only thing I can now show you as an actual example is a simple code that will just, in every MPI process, will initialize a number with their own MPI rank, and then they will shift it to the next neighboring process, and that process will then go and print the variable that got communicated over the network. So extremely simple example. And in the example, I have two codelets. The first task types, the first task type will just go and get a variable that has been passed to it. It is just an integer, and it will just set the value of variable to its own rank, which has been extracted from the MPI. And then it will go and print the number that it went and stored into this data handle. So in that case, the rank number I, it is just going to store the number I to this data handle here. And the second codelet that I have is just going to get a data handle. So again, it is going to extract the integer pointer from this data handle that's been passed to it, and then it will print its own rank and also the value of the handle that it was given. And inside the main routine, we have pretty typical stuff. We will initialize MPI, we will initialize StarPU, and then we will also initialize StarPU MPI. So what happens at this point is that StarPU will just take one of the cores and put a special thread running on it that will do the MPI communications. And the next thing is that we will just ask what is the current world size, so how many MPI processes we are running in total by calling StarPU MPI for world size. And then we will initialize a table of data handles. So for each data handle, we will call StarPU variable data register to register a variable type data handle, and we will store it to the corresponding element in this array generated here. we are telling it that this data currently does not have a home node. So we are just telling StarPU that this is a placeholder data handle. It will be initialized. It may be initialized later on, or it may not be initialized. And when we do it like that, we also have to pass it a null pointer to indicate that we are not initializing this particular variable right now with anything. And then we are telling it that this is just an integer variable, its size of integer. And then we do additional thing where we also say that this particular data handle is going to belong to the MPI rank number I, and we will also give it a unique tag, which in this case, it's just the same as the owner of this particular data handle. And this is done on every single MPI process. So all the MPI processes at this point have data handles for all the involved variables, and they are just initialized as a placeholder variables. The next thing is that we will loop over and insert a task for each MPI process, and we will call StarPU MPI task insert and specify the communicator that is used here. By default, is this just MPI com world, and we are specifying that it's going to be this write number type of task that is simply going to write into this data handle its own MPI rank. The next argument is where we specify that the MPI process that will actually execute this task is going to be that the MPI rank that is the owner of this particular data handle. So even though we insert this task on every single MPI process, there is just one MPI process that will actually execute the task. Every other MPI process simply knows that such a task has been executed on this particular node. And then we'll just pass that we are saying that this task is going to write to the corresponding data handle and then terminate the function call. And the next thing is that we will insert a second set of tasks again in every single MPI process. And this time it is going to be this read number codelet. So the task that is going to simply output the contents of this particular data handle. And in this time, we are forcing it so that the MPI process that will actually execute this task is going to be process number I. And this leads to a situation that, again, these tasks are inserted in every single process, but only one process that whose MPI rank corresponds to I is going to execute it. So just one. And then we are telling it that we are going to be reading from the variable here, and we have to shift it so that instead of reading the data handle that corresponds to this particular MPI process's rank, we are just going to +1. So we are going to be reading the data handle that corresponds to the neighboring MPI process. And then what remains is that we will unregister every single one of these data handles. And then we will shut down everything as before. And the output looks like follows. So only thing you have to add here is that also link the StarPU MPI library here and also MPI library to make it to compile. And then you see that rank number 1 is writing its own rank there. Rank number 0 is writing its own rank, same for 2, and same for rank number 3. And then when you look here that rank number 3 reads value number 0, rank number 0 is number 1. So we get the correct result out. And the only thing you know that is missing here is that no point did we actually communicate anything. It is all done automatically by StarPU because we have told StarPU here that who owns the given data handle. So when we are inserting the first set of tasks here, then every single process knows that there at some point something was done to this data handle, and it is currently located on this MPI process. And when we insert this next set of tasks here, what will happen is that all the tasks that now need the data handle from some other process, they know to do the receive call, and then every process that actually owns the data handle knows that they have to do the corresponding send call. So this is just a simple possible example I managed to imagine how to demonstrate StarPU MPI for you people. And again, this is a bit more complex at this stage than doing a simple similar example using an MPI directly. But you must also consider that when you have a more complex code, then the actual amount of code that goes to communicating will become much more complex. Whereas in case of StarPU, there is nothing in the codelets themselves that relates to MPI. They will just get pointers to somewhere where StarPU is guaranteeing that we have the data available. And when we insert the task, again, the only stuff we actually have to do is to tell where the data is located, and then in some way specify who is actually executing the task in a consistent way. So I can either tell it that we will just use this data handle here to specify who executes it, or we can directly say that it is going to be this node that is going to execute it. And there is no need to do any communication here. And on top of this, StarPU also implements a cache that makes sure that we don't redundantly communicate the same data handle multiple times. It will communicate it once, and only if it gets modified later on, it will be communicated again. And that this can cut down the amount of data traffic considerably. And now the only remaining stuff to discuss is the accelerators. And again, unfortunately, we don't have time to cover it in any great detail. But just a reminder, when you look at this code, StarPU code struct, you remember that we had this array that allows us to store a set of Cuda implementations for this codelet. And just to show the simplest possible example, what I've done here is that in the codelet, I've specified one additional implementation for this codelet. And in this case, it is a Cuda implementation called Hello World Cuda that is implemented here. So it has exactly the same prototype as the CPU implementation here. So in that sense, these implementations are very similar. But inside the Cuda implementation, what I'm doing is that I'm asking StarPU to give me the local stream for this task. So StarPU maintains local stream or command queue for each GPU to which we can then insert Cuda kernels. And the next thing is that I'm inserting a Cuda kernel into the stream here. And what the kernel will do, it will just perform a printf on the GPU, after which I'm waiting for this Cuda kernel to finish by calling Cuda stream synchronize with the stream. And at the end, I'm just checking for any potential error codes that might come out of it. And beyond that, actual main routine, nothing changes. We are simply inserting the task and then telling the code that is going to tell StarPU that there are two implementations, one for a CPU and for a GPU. And the decision which one of these actually gets executed when it's time to execute the task is then left for the runtime system. And you can see that if we can run this code and then we are relying on this default very simple scheduler called Ecar, in that case, what is happening is that it will always end up executing the CPU implementation, because this Ecar scheduler is a scheduler that will just execute the task as soon as they become available. So it doesn't really even consider priorities in the right sense. And it has no concept of GPUs. And it will just pick the first implementation it can find. And it just happens that that implementation is the CPU implementation. But if it switches to a slightly more complex scheduler that tries to use GPUs, in that case, it actually might go and pick the GPU implementation to execute instead. And the main reason that I'm saying that this is a very simple example that doesn't really tell you that much how to use the accelerators in practice is that what we are missing are so-called performance models. So in order for StarPU to make intelligent scheduling decisions, you must tell it that what sort of performance models it should use to predict execution time. So in the StarPU codelet struct, we have a field called model. And this model is supposed to contain information about the performance model that the StarPU is supposed to use with this particular type of task. And in the simplest case, you could just say that the StarPU should use a history information. So every time StarPU is executing this type of task on a CPU and GPU, it will record the runtime. So it could use this history information to do that. Or then you could use something more complex. You could, for example, use some sort of linear or nonlinear regression model, or even multiple regression models to do it. And when using any of these, StarPU has to know what type of task it is, and it also has to know how big the task is. And by default, StarPU will just take all the data handles that the task is using and compute the total amount of data involved in these data handles. And from that, it will get to estimate how big the task is. So it knows that if the task size was 10,000 earlier and it took 5 seconds, then it knows that next time this task is running with the size 10,000, it will again probably take the same amount of money time. And in more complex situations, you can implement this so-called base size, so a function for which you're passing on a task, and then it's going to tell StarPU how big the task in whatever sense it's more relevant for this particular task type. And this is the main reason why I'm not discussing the GPUs more than this here, because this is a very tricky topic to get the performance models to work correctly. And then also, it's also often bigger issue to go and get the task granularity right. Because in some cases, for a CPU, you want to cut everything to reasonably small tasks because you have quite many CPU cores in a modern machine and you want to keep them all busy. But you usually have to use 1 or 2 or 3 or 4 GPUs on a machine, and for those you want to cut the things, the commutations in the bigger chunks, so that you can actually get the better performance out of it. And this is turned out to be extremely tricky thing to do, and it's specific to the algorithm you are implementing, and that's why I'm just telling you the very basics, and then you have to go and experiment yourself and see what would make sense. Does it make sense to run stuff on the GPU or not? But once you have done those initial decisions, then StarPU can, in several cases, do these decisions very well, and actually you will get a reasonable speed up for your code when you're running the GPU. And this now ends this lecture here. I believe that I had your right now I had just one more complex hands-on for you to do. And after this lecture, once you have finished this hands-on, then you can go and look at this ALU factorization example. That is pretty much the same thing you did yesterday just before lunch, but you are just supposed to do it using a StarPU and see how well things would work. And since both of these hands-ons are quite involved, I will now just give you the rest of 1 hour to try to do these hands-ons, and I'll be monitoring here and seeing if there are any questions. And otherwise, I was really happy to see many people here for this course, and I was really pleased that there was some interest for this topic. And the recordings and the materials are going to stay available if you want to go and recheck something, or if you, for some reason, didn't have time to participate on a particular day, the final recordings will show up probably tomorrow. And then, of course, the last thing is that I would hope that people would go and fill in the course survey, because this is a course organized by HPC2N, but this is a praise course that's available for people across many EU countries. And praise wants to have some sort of information how people like these courses. So please go and fill the survey. It is quite short. I believe that it takes something like 5 minutes to fill it in. It's mostly just multiple choice, and there are a couple of fields where you can write more comments if you want. Otherwise, I will be waiting here for now until noon and see how people are doing with the hands-ons.